everybody for being here. I am pleased to introduce Dr. Hamze Dokoohaki. Hamze is an assistant professor of digital agriculture at University of Illinois. He received his PhD at Iowa State University in agronomy and also did a postdoc at Boston University before starting at the University of Illinois. His research focuses on developing novel data-driven approaches at the interface of computer science, statistics, and crop science with the goal of improving and protecting our food production systems. So thank you for being here. And the title of the talk today is Model Data Fusion for Monitoring and Forecasting Agricultural Systems, Opportunities and Challenges. Thank you.
Hello, everyone. Happy birthday. Just remembered. Thank you for having me. So excited to be here. My name is Hamze, assistant professor of digital agriculture from the University of Illinois. And today I brought a presentation with myself, which is showing most of the work that we did in the. Yeah, I can't stand it, so I'm sorry. I'll be posted it on. Most of the work that I'll be showing today, honestly, was done in the darks of code and inside our own labs with just only students. And I'm so excited for the first time to showcase the work that we've been doing. And I'm hoping this will open up the conversation in a bigger context of the prediction problem in general in agriculture. Today, I'm going to take one step back and think and talk about different ways of monitoring and forecasting agricultural resources. And I'll be offering a new mathematical framework, propose a new mathematical framework that we think can provide a complete solution to model data integration in agricultural systems. And I'm hoping we could have a pretty nice discussion afterwards about the application and the use cases for these systems. Well, to set the background, either we acknowledge or not, there is a race, scientific race, to develop systems that could monitor and predict agricultural resources and crop production at a regional scale. And that's important because simply that defines how much food supply a country has, and that defines sort of the balance between the supply and demand. And we know that the crop production right now is this, at the core of this, what's called the perfect storm of facing so many different challenges ranging from climate change to geopolitical tensions nowadays that are impacting the security of food supply at a global scale. And this has been the challenge of our 21st century, to produce enough food that could ensure nutrition security at large scales while sort of preventing loss of biodiversity before doing this kind of crop production. But we know that data-driven decision-making and regenerative agriculture practices, they can help us in the face of these challenges to maintain and improve agricultural productivity while reducing the adverse effect of these challenges. But the problem is that field experiments alone are inherently limited in providing precise recommendations or predictions across diverse G by E by N scenarios that could help us to discern between the side effect of these different regenerative agricultures with data-driven decision makings. We were talking about this earlier in the morning, that this is so sad to think that if you don't have a field experiment at a subsection of G by E by M, it is really hard to make good predictions and make good recommendations without any field experiments. That shows us the gap, and we know the predictive models have been around for a few decades that can help us potentially provide precise predictions or recommendations that could let us to discern between the benefits of these different management practices. But what are the different competing approaches to agriculture, predicting agricultural resources? We have two different competing approaches. The most commonly is machine learning models. And some of the problems with machine learning models is that, first of all, they lack generalizability. And by that I mean that if you have a, for example, measurement of soil moisture, you can say nothing about how the tidal flow drainage changes. You're always limited to the domain of the data that you collected. At the same time, they're very data hungry. They require a lot of data to be trained so they can provide precise predictions. While they're data hungry, they lack mechanics. Like they use the data to make predictions, but they don't tell you how they did it. And finally, they have meaningless parameters. I don't know if you're familiar with GTP3. This is GTP3, the state-of-the-art next generation AI developed by OpenAI that can communicate with you. It's hard to even recognize this AI, writes essays. And this model has close to 200 billion parameters. And this is a place that we need, as an agricultural scientist, to stop and think that, is that where we want to go? And is that the most efficient way of using the data that we're collecting? What pros are is that these models work really well in a very constrained parameter space in the G by E by M. Like if you have enough data, you can actually extract a series of correlations, covariances, which is really important. They're easy to develop and they're computationally cheap. They're really fast. On the other hand, we have process-based models. For those of you who are not familiar, process-based models are, you can think of them as a mathematical blueprint of how a cropping system may evolve, soil processes, crop processes, and their interactions with each other. But simulation of each of these different pieces in soil, crop, and their interaction requires its own series of inputs, parameters, and sort of its own structure. That ends up producing a lot of uncertainty that comes with the model structure, with the model inputs, with the model parameters, and so on. At the same time, they are computationally very expensive. It's really hard to, it's not hard to run them, but computationally, compared to machine learning models, they take a lot of time, memory, and resources. And finally, it's really difficult to develop these models. The current state-of-the-art process-based models that are out there, DSAT, APSIM, it's been taking decades for the developers to get those models to where they are right now. And it's still, they are pretty uncertain for the predictions. If you want to talk about pros, what makes these models attractive, maybe the most important thing is that they substantially need less data compared to machine learning models. And since they encode our understanding of the processes inside themselves, the mathematical equations, they already estimated the covariances that we wanted to spend so much data in machine learning models to estimate those covariances. And those covariances come from thousands of the studies, field experiments in the literature that these developers have collected over the time and compiled and let them to talk to each other. And finally, they have meaningful parameters. Parameters in these models have a biophysical meaning. That's why it makes, in my opinion, it makes much more sense to invest your money and time to collect data that's being used and ingested more efficiently by process-based models. So the work I've been doing since graduate school and now in my team right now is all of them are using process-based models as the base predictive layer for our analysis. But when it comes to process-based models, the moment we want to plan to use these models, we are faced with this dilemma, the model complexity dilemma. That in one hand, we have simple models that simplify models in the interest of generality, but they don't scale up or they're limited, very limited in their inference space. On the other hand, we have complex models that they admit the complexity to attain a level of realism, but at the same time, there are so many uncertain equations in these models that makes you think that they're overfitting in most of the cases, and they're uncertain in their predictions. But we believe that stochasticity, or propagating the uncertainty, is the central to this dilemma. If you would be able to admit the parts of this model that you don't know, admit the uncertainty, admit the lack of knowledge, and propagate your uncertainty in the parts that they are uncertain, and keep the parts that they are more certain, deterministic, then the prediction made by these models are way more confident and robust compared to each of these cases. And this is common actually in the statistical learning. If you're familiar with ensemble learning methods that they use different model realizations, starting the model with a slightly different input parameter or different structure has been widely accepted and used in the statistical learning. The idea that a group of what's called weak learners can do better than one strong model has been accepted and is used in literature and in statistical learning a lot. Examples of that, for those of you who are familiar, bagging, boosting, stacking, random forest, meta models. The idea behind all of these models is that how can we have a group of models, weak learners, that they just do slightly better than random, but in all together they leverage the wisdom of the crowd. And it's been shown that for process-based modeling, they improve predictions substantially in both levels of calibration, high and low. But they require uncertainty propagation techniques. Monte Carlo sampling methods or family of Monte Carlo sampling methods are some of the most widely used methods for propagating uncertainty in process-based models. And that's then the first step to admitting what you don't know and then plan for controlling or constraining the parts that you don't know with some observational data. At the same time, it's really important to know how this uncertainty really propagates throughout the model, because it helps you to find the next best logical steps, or it helps to find the choke points in a model where the model doesn't know or has the largest source of uncertainty. Then you can focus your time, energy, and your investment in the exact parts that the models are not doing the best. So to understand how different source of uncertainty propagates, I looked at the 5 different individual sources of uncertainties in process-based crop models when they are used across larger scales. Initial condition, soil properties, meteorological forcing of weather data, management data, like planting, how much fertilizer you should put, when to put it, and model cultivar parameters, and trying to see how this uncertainty propagates into estimating corn yield across the region. And we found that management and parameters are the largest source of uncertainty and the most sensitive source of uncertainty. But the most exciting part of this for us was that we found that the interaction between these sources of uncertainty sometimes are more important than the individual sources alone. So what I'm showing here is that this is uncertainty in soil properties, uncertainty in management properties, and this is basically uncertainty in crop yield. And you can see that there is a large correlation between these sources, meaning that if you don't know the management and you don't know the soil, the uncertainty that you get in your crop yield is larger than any of them, just some of both of them, meaning that they interact with each other and they increase the amount of uncertainty in total. But one of the advantages of admitting this uncertainty, this lack of knowledge, is that now you can, instead of working with single model predictions, since you have now different model simulations with a slightly different inputs, now you work with distributions instead of single model simulations. And when you work with simulation, you can ask very interesting questions, like the probabilities of events happening. And probabilities are really helpful for deciding or determining actionable decisions. So what I'm showing you here is a cover crop simulation that we did. The start date of 2000. 2000 to 2005 was a spin up. The resolution is 5 kilometer by 5 kilometer across the state of Illinois. This is a corn system. And we propagated the uncertainty in weather data, soil properties, management practices, and model parameters, cultivar parameters in cereal rye. And we explored the probability and expected value of corn yield increase and soil carbon increase. Then we classified our probability and expected value into 4 classes. The dark color here is the most optimal scenario, high probability, high expected value, and the light is low probability, low expected value. Meaning there is a less probability of seeing yield increase, and even if you see that yield increase, the expected value is small. So the yield increase is going to be small. And the same for soil organic carbon. And then we tracked how this class of optimum scenario changes over time, 2010, 2015, 2020. And the goal was here to make recommendations for people. If you're planning to make an investment in having plants and cover crop, you should have an idea that how long does it take for you to see and invest in your return in your investment. At the end of the day, but then the question is that these uncertainties need to be constrained. And at the end of the day, these uncertainties needs to be constrained with some data, observational data. And so the question here will be more like, how are we supposed to integrate models with data? And this seems to be a question that's on mind of so many people. This is a very recent paper, November 2021, the chaos in calibrating crop models. It's a very interesting study. 29 different groups participated in this study. They all given the same exact data set, and they told them, however you like, calibrate the model. And I brought this quote, I thought it was really saying about the state of model data integration in the field, that it says, it seems that we're far from having a consensus on how to calibrate crop models. Even in relatively simple cases with only phenology data, which emphasizes the need for calibration guidelines. That kind of shows really clearly that we need a robust mathematical framework that would help us to incorporate observational data into process-based models. I'll be talking about 2 complementary approaches that we believe together, again, can provide a complete solution to this problem. And I'll show you a couple of the works that we have done with these different methods. The first step that everybody's familiar with is what's called the parameter data assimilation. This is what people historically have been seeing as calibrating model parameters, and the first step, and also the last step in constraining model uncertainties. And there is a ton of paper in the literature that you can see, you can find talking about this topic. But the problem is that when you only assume that only a step in constrained model uncertainty is parameters, that makes the assumption that you believe the model is perfect. The only source of uncertainty is in the parameters. And if parameters are certain, then you should be able to make perfect simulation. And by definition, no model is perfect. At the same time, model calibration doesn't correct for model structure error or input error. And I bet when I say this, you probably ask yourself, why would it? But inherently, we're using a method to integrate data into crop models that is only concerned about the parameters. Let me give you an example. You're trying to calibrate the model to make good simulations of soil moisture. And you have systematic bias in your precipitation. And you spend so much time calibrating the soil properties. Of course, no matter how much time you spend, you're not going to be able to have any meaningful improvement in predictions because the source of uncertainty, the source of error, is not in the parameters. At the same time, there is a risk of overfitting or what's called the equifinality, meaning that different combination of values for these parameters can provide exact same outcome. Meaning that you don't know what that parameter it is. What is the real value for that parameter? It also, at the same time, has a very limited potential for further model evaluation and improvement due to carryover effect. Your error in today's simulation could be the error from the previous day that's being carried over to today, or it could be a whole error in today's simulation and yesterday's prediction could have been perfect. So there is no way of truly understanding how the error propagates. Another topic that I had very interesting discussions today with a couple of different faculties about this is that it's not also straightforward how to share data between sites and years. If you have collected data across a bunch of sites and a bunch of years, one way is to calibrate each site individually, making the assumptions that sites are independent. Or on the other hand, you can imagine that there is all of those observations was collected only in one site and there is no site-to-site variability. And there is some in-between methods, hierarchical models, mixed effect models that can acknowledge the site-to-site variability, but allow for sharing information between different sites. I'll give you an example of how the sharing information across sites really works. And finally, I promise you, this is the driest slide I have. Next slide is going to be more exciting. Historically, people have been only using field data for model calibration. And we know that inherently field experiments are expensive. We cannot afford to run field experiments everywhere and collect data. And there's a question of real use of remote sensing application in calibrating process-based models. So constraining model parameters or only calibrating models alone is incomplete, at least. And we'll show you a complementary framework, mathematical framework, that we think can solve all of these long list of deficiencies in model calibration. So I tried to answer some of the questions that I put forward in the previous slide. I asked the question of if the remote sensing has enough information contribution to be used for calibrating process-based models. And if they have enough information, how are we supposed to share data across large number of sites? So what we did was we did a global sensitivity analysis to find out what parameters are controlling leaf area index in the APSIM model for corn. And at the same time, we extracted LAI from Sentinel-2 and DVI from Landsat 8, and then use these two at the same time to constrain the model parameters. But instead of running a model itself, because the model is slow and expensive to run, we use what's called emulators or surrogate models, which they try to replicate the behavior of the process-based model in a constrained inference space. So if you only develop these models in the parameter space that you found as the most sensitive parameters, you can fit these gap models, and they are by far faster running than the absolute model itself. And when we calibrate the model, we can evaluate the performance of the model on correlate. Here's a distribution of the sites. I used 13 sites across the US Midwest for calibration, and then I evaluated the model across over 400 sites. The data set is coming from the Beck's seed company data set. Here is the calibration of the leaf area index across all of these different sites. And different colors here show different methods of sharing data between different sites. So for example, you can see that here, this is a really good example for sharing information between sites, that you can see the blue site level where sites are independent, only the observations in that site is used to calibrate that site, shows the largest uncertainty in LAI prediction across all the sites. But in hierarchical Bayesian methods, the uncertainty is much less compared to the blue one, because we are sharing information from the sites with higher number of observations, but we're acknowledging the site-to-site variability by including side effects into our analysis. This is a final validation table for the only 2 years that we calibrated. So another phase of this project was that, can I use the parameters that I calibrated in an environment, in a region, and take them into a different region? Or can I use parameters that I calibrated in some years and use them in different years? So we calibrated in 2018 and 2019, and we showed comparable results in model accuracy of crop yield compared to field experiments. We also investigated the information contribution of NDVI versus LAI. And we found that literally LAI carries the analysis on its own. At the same time, we were not interested as much to constrain too much these parameters because of the same problem of equifinality that I was talking about. And we're attempting to capture the leftover uncertainty, constrain it by what is called a state data assimilation. This is the technique that I was talking about, the framework that I mentioned before. At the core of a state data assimilation is a cycle of forecast and analysis based on the Bayes theorem. So these different shades are different models with different realizations that are run. And this is the mean prediction with its uncertainty at time t. If you have observations, if you have a bunch of observations for same state variable with a mean of y and uncertainty of r, we can use this as a prior and likelihood. You can use this as a likelihood and estimate a posterior, and then run the model from the posterior instead of what it used to be. This mathematical framework was first suggested for numerical weather prediction, and it's known to be responsible for the major sort of improvement in prediction that we have seen in the past few decades. And basically so on. Next time step, you make a prediction. The next time step, you have wait for observations. When observations come online, you find the middle ground. You can think of this as a weighted average, which each piece is weighted based on its precision or its uncertainty. This method is complementary to parameter data assimilation. Why? Because it can inherently allow for correcting in model inputs and model structure. If you have a biased precipitation error that force your model to make to overestimate the soil moisture, If you have real soil moisture that doesn't have the bias in the precipitation, then this automatically adjusts you and gets rid of the uncertainty in the inputs. This is actually a very interesting method for localizing gridded data products for one specific location. But the most exciting feature that SDA offers is that it can allow you to leverage the covariance between the state variables. Not only you can constrain the variable that you have data on, but you can also constrain the variables that you don't have the data on, but they're highly correlated with what you have data on. I'll show you an example. This is very useful for soil carbon and soil carbon analysis. That if you think of soil carbon as at a global scale or continental scale, we can make we can have observations of the above ground biomass and make easy measurements of other pools in the soil carbon cycle, but not the soil carbon itself. But we know that these pools are highly correlated. We can leverage that covariance. And because of that, we say other state variables are not also going to be blindly forecasted. The last point about SDA, sequential data assimilation, is that observations now could be anything. It could be field experiments, it could be flux towers, it could be remote sensing. And you can think of this mathematical framework as a scaffold, as a way of connecting and letting these different data products talk to each other, remote sensing, field experiments, flux towers, something that had not been practical before. We can at the same time also follow the trajectory of each of these ensembles and learn from which one of them does better, worse, and so on. So what does SDA generate? The most important thing about what SDA generates is that when it's applied across regions, the data product that's produced is called reanalysis data product, and it has lower uncertainty in the reanalysis product than either the model or the data alone. This is the key to understanding why sequential data assimilation is complementary to parameter data assimilation and a key crucial tool for constraining uncertainty in process-based models. The second advantage is that reanalysis data product can be updated real fast because this is a posterior, and this posterior could be a prior to a new data set that you might find or could become available. And finally, same thing, since we can leverage the covariances between different state variables or even between different sites, we can not only constrain the estimated value of a simulated state variable, but other state variables as well. So I'm going to show you two different studies. This is hot out of oven, literally was published yesterday. Develop an open source regional data assimilation system in PCAN 1.72, application to carbon cycle reanalysis across the CONUS using the SIBNet model. The method was pretty simple. We used a very simple process-based model called SIBNet. I'll show you in a second how does it work. I didn't talk about the mathematics of how data assimilation works, but specifically, we use ensemble common filter. Excuse me. And the input drivers are weather data, Aero 5 from Europe with 30-kilometer resolution, initialize the model with Meriflux data and GSorgo for soil properties. And here's how the carbon cycle in this model looks like. We have three pools: plant wood carbon, plant leaf carbon, and we have soil carbon. And we know for a fact from the mechanics of this problem that these pools are highly correlated with each other. So what we did was, in the first step in the parameter data assimilation, we used latent heat flux and net ecosystem exchange from Meriflux sites to constrain the parameters of photosynthesis and respiration, autotrophic and heterotrophic respiration. And when the parameters are constrained in hierarchical Bayesian method across 7 sites, we assimilated Landsat estimate of woody biomass into the plant wood carbon and LAI from MODIS into the plant leaf carbon. And the goal was to see how much we can constrain the soil carbon. This is a short animation of how this data assimilation works. So we make one forecast in time. This is above ground biomass, LAI, and soil carbon. We make one forecast with yellow. We wait for an observation to come online. We simulate that observation. We start from that point to the next time step and repeat the cycle. And you can see that initially we have good constraints around LAI and soil carbon. The difference between the yellow and green would tell you how much each of these pieces were able to constrain the soil carbon. And at the end, also, when we get measurements of LAI, both of them combined can help to systematically and substantially reduce uncertainty in soil carbon estimation. We did this analysis for 500 sites, all at the same time. We leverage the auto covariance, spatial covariance, not only in time, but also in space. So sites with observations could help with sites with no observations if they were close enough. And this is an example of one of the analysis in the science that you can see. We have a very wide forecast, and then these are getting constrained using a state data assimilation. What we found in this study was that we did this analysis for 5 different plant functional types. And we found that our sites and agricultural sites in the US Midwest are not doing well at all. We're not able to constrain soil carbon in those sites. And the reason for that, it was pretty obvious for us, because we knew that the model that we used was so simple, lack of implementing management practices, lack of strong soil water module, lack of nitrogen module. So there were so many different reasons to believe that this model is not going to do in agricultural sites. And the reason for that is that these cycles are tightly coupled. You cannot constrain one cycle without having a good grasp of how constrained are other cycles that are controlling the carbon cycle at the same time. So for example, here we have a water cycle. We know it's connected to the carbon cycle through water uptake in the plants, and the carbon cycle is connected to, coupled to nitrogen cycle through N uptake and through N uptake and mineralization and immobilization. But we have now a couple of different questions that we have to ask ourselves. The question is that now that we have this tool, are we supposed to constrain all of these state variables that we have observation for? Or how much improvement we can gain by constraining each of these state variables? Maybe there are a few choke points. Maybe there are 2 state variables. If they would be controlled, maybe one between N uptake or mineralization, or one water uptake, it could substantially reduce in process-based models. We don't know that. And that's as a function of how the process model is structured. So to look at that problem, we did develop another state data assimilation system, but now this time using the APSIM model. We built it on top of the APSIM model. And we tested it in a farm, 2018, 2019, soil moisture measurements of the 10 centimeter, 20 centimeter energy farm in Champaign, 2018 corn, 2019 soybean. Constants are the things that we had exact information on it, and uncertainties are the ones that we propagated the uncertainty into the APSIM model. I don't want to get into the technicality of how these systems are developed, but if you would be interested, we can talk about it in the Q&A section. But there are tips and tricks that you need to keep in mind when developing these systems. What did we learn by assimilating soil moisture? The first thing that we learned was that assimilating soil moisture, in situ soil moisture from soil sensors, helped us to substantially improve soil water prediction at two different depths. So this is time series. On the x-axis, we have time, and the y-axis, we have soil moisture, 10 centimeter, 20 centimeter. Dots are observations of the soil moisture, and pink or red is absent model alone without any help, only calibrated, and different shades of blue are different flavors of state data assimilation. You can play around with the statistics of the problem, letting the soil properties to be dynamic throughout the time. This was one of the things that we tested. But the major improvement that we got was only from moving from free model to state data assimilation. Not only improved prediction by 44%, but also reduced uncertainty almost by 40% as well. What else did we learn? We learned that this improvement in the model, it propagates through the processes. So it at least propagates through the vertical soil profile. So the improvement in the 10 centimeter and 20 centimeter, now we can see similar levels of improvements in 70 centimeter and 120 centimeter. The free model RMSE for 80 to 140 centimeter is 0.14, but with SDA, this is reduced almost by half. And the same thing for the variance. We're able to reduce the uncertainty in prediction of soil moisture in deeper soil layers. Why is that important? Because that defines the tile flow drainage. And if you can make a better simulation of deep soil profiles, you can make a better prediction of tile flow drainage and nitrate leaching. So tile flow drainage, again, observed is the black, blue is free, and pink is the state data assimilation. We call it PDA here because of different reasons. We can chat about it, but we can see that we could improve the daily tile drainage by 23%, increase the precision by 42%, and accuracy by 43%, in the cumulative, annual, and precision by 43%. What model is not doing well? Is it? There are still large sort of differences between model predictions and observed. But it's still, if you think about it, we went to this analysis with no prior information about tile drainage. And we made these simulations that at least they totally follow the pattern of the data. And they made a major improvement in prediction of the tile drainage. This was 2 years, what I showed you, and one site. How about if you expand this into more sites? Now I have 19 site years across US Midwest, and we did the same analysis. We tried to see if this can find the same behavior. The data came from the Transform Drainage Project. And what we found was that exact same thing. Cross different sites, we were able to improve soil moisture predictions. The improvement propagates vertically through the soil profile. We can improve NDVI and yield. And finally, we can also improve drainage. But what was the most important and interesting out of this analysis was that the improvement that we got in the yield prediction mostly came from the years with extreme events. The model was failing in 2012, 2015, and here in 2016. And in all cases, what you see blue is the free model with no help, and red is SDA. Only assimilating soil moisture, nothing else. Still, we saw improvement, major improvement in yield, at least in the years that we have substantial water stress. Finally, we repeated the same analysis now with remote sensing data, 4 different data products, SMAP hydroblocks, 30-meter resolution. We had 162 data availability is 162 days per year. ESA CCI, 25 kilometer by 25 kilometer, SMAP Sentinel-1, and then what if we combine all of them at the same time? Let all of them to be used in data assimilation. That's another interesting about data assimilation, that multiple data products at the same time can inform one state variable at the same in the model. And we saw improvement in model predictions of NDVI, yield, and reduction in variance also at the same time in all of these cases. I'm getting to, we're getting almost to the end of the hour, so we'll go through some of the future directions and my final thoughts in state data assimilation. But the future direction in my lab, I'll be investing a lot of time and money on understanding how can we explore the effective data assimilation of remote sensing observations on water cycle, carbon cycle, and nitrogen cycle. And there is an opportunity for coupling SDA with machine learning models, where it turns out that machine learning models can predict the residuals coming from state data assimilation systems really well. So stack layers of process-based models, state data assimilation, machine learning models can at the same time help to reduce the gap and provide precise predictions that we need for discerning between different management practices. Our goal of the lab is to generate the first kind of pass in regional data assimilation or regional reanalysis data product across the Midwest by assimilating these different data products. We have already started this project, haven't had enough results for me to bring it today. But we have observations in almost all of the cycles: carbon cycle, nitrogen cycle, water cycle, remote sensing observations that could be leveraged and assimilated into these systems. There is an opportunity for use of high resolution imagery to capture within field variability using SDA. These are some sort of advanced notes on state data assimilation, which I thought if someone wants to work on it, it's good to know these maybe ahead of time before getting into this. The first one is that, again, SDA allows for iteratively learning as the new data becomes available. This was something that we talked about it before. The second point is what's called the state augmentation, where you not only try to constrain your state variables, but you also try to constrain your parameters at the same time. And I showed you one of the cases in the soil moisture where we allowed the bulk density of the soil to vary throughout the growing season. The parameters that's always constant in most of the process-based models. But we know that there are a lot of different reasons for bulk density, the physical properties of the soil to change throughout. We think there is a great potential for connecting radiative transfer models with these process-based models through state data assimilation. This means instead of translating satellite imagery to NDVI or LAI or something that crop model is supposed to understand, taking the crop model to understand the reflectance, simulate the reflectance as a function of canopy architecture and soil moisture using the ProSail model. For optical data and water cloud model for SAR data. When you use SDA, you're always at the most optimum state of the system. Then it puts you in a really good condition, it's the right situation to make forecasts. You have the most optimum initial condition to forecast into the future, because most of the uncertainty in forecasting the future comes from the initial condition. And that's why these systems can seamlessly transition into short-term or long-term forecasting. The problem with them is that mass balance is not respected. Mass balance is not respected could be a challenge or blessing in disguise. If SDA wanted to respect mass balance, then the systematic bias in precipitation would not have been adjusted. And finally, estimation of model error, because what you find as a middle ground is a weighted average of these two pieces of information weighted by their precision. Then knowing what is the error or precision of each of these pieces is extremely important and actually the determining factor in success of these state data assimilation systems. That's all I had for today. I hope you enjoyed it. I'm open to questions.
In the very beginning, you talked about one of the cons of machine learning being that it wasn't generalizable. So, I mean, the scope of inference of like traditional statistical models is constrained by their, like the sample. Is it different than that, or could you explain that a little bit more, please?
Yeah, so by the generalizability, I meant more that you're stuck in the domain of observations that you have. Again, if you have soil moisture, you can only make predictions about soil moisture and try to understand soil moisture, but nothing beyond that. Versus when you start using process-based models, since the relationship between these state variables is already embedded in them, you don't need observation to go from soil moisture to time drainage. That's already basically there.
Okay, I see what you're saying. So it's really not that different than like statistical inference, the way that would be constrained.
Yeah.
Okay.
What frequency of data you use from satellite or remote sense data to feed the model?
Frequency. Based on their availability. Whenever the data comes online, we have that observation, we would assimilate it into the model.
But do you have like several points during the growing season?
Yeah. So in some cases like ESA, we have a full, maybe every other day observation, but the problem is the scale, spatial scale. But it is very interesting because we found out that temporal frequency might be even more important than the spatial resolution. But again, we're really early into use of remote sensing to constrain models. We need to dig into this a little bit more.
Are some of the variables that you are using related to crop and nitrogen, or more biomass, urea index?
For prediction or for observation? For constraining models?
Some of the canopy indices or satellite data that you're
Yeah,
using, some are you using them to calibrate nitrogen balance, or more focused for now in urea index, carbon balance?
We have not yet tackled the nitrogen cycle. And my guess is that it's the most difficult one. So one approach that I was thinking about incorporating information that we get about nitrogen from remote sensing is the use of ProSail or radiative transfer models. Their input is information about architecture and nitrogen content and LAI canopy cover of the canopy, and they simulate the spectral signature. And what I've seen in the literature about inverse modeling of ProSail, because now inverse modeling is that you have the reflectance, you want to know the nitrogen. It is really hard to get any useful information out of it. And I have not seen any, I have not seen very successful applications of any model basically to get nitrogen information from the remote sense. Not generalizing.
So is that just because it's kind of whatever the remote sensing is measuring could be more than one thing? Like it's,
Yeah, the signal is mixed with different factors. The most important ones are AI, magic hunting, the story much. You basically have three unknowns and one known, and figuring that out is the difficult.
Do you think working with data from drones will help link from models with ideal imaging, because maybe it will be more detailed
Yeah,
or scaling up to satellite data?
yeah. So for those of you, I don't know if you could hear the question, I forgot, sorry, I should have repeated the other questions. The question is that if there is any difference between drones and satellite imagery. My suspicion is that the caveat or the choke point is the spectral information, not the spatial information or temporal information. We need more samples from the spectral signature of canopy to then more and more precise. Because, for example, Landsat gives you 4 measurements. Drones usually RGB, maybe 3 to 4 measurements of different parts of the spectral signature. But different compounds like chlorophyll respond to the part of the spectral signature that's between red and near what's called red edge, which a lot of different satellites, they don't have a measurement of that. Drones, most of the time, unless you put down a lot of money to get a good sensor to make that measurement, or you knew beforehand that you have to have that. So yeah, I think this needs to be looked at, but my suspicion is that spectral information might be the most important piece.
So is Landsat not collecting the full spectrum? It's only collecting a few spectral lines, or?
Yeah, bands to me are different samples of the spectral signature.
Yeah.
And Landsat has maybe 7 or 8, which 2 of them, the first 2 are in the blue region of the wavelength, completely useless to agriculture. Crops don't respond to it. And there are a couple of different bands, band 11, maybe band 12, that are way into the long wave, again, not as useful. My experience, I didn't show this here, I'm trying to use Landsat and VIIRS, which has 30 different bands to estimate soil moisture in a similar setting. I learned that Landsat cannot provide enough information for you to distinguish between soil, water content, and LAI reduction.
Is that like a function of the design of the detectors, or is it like a data transfer thing? Or?
No, it is. Yeah, it's a design. I have heard that Landsat 9 was launched past November. It's a copy paste of Landsat 8, same number of bands. But I think the next Landsat, which is actually called Landsat Next, is going to launch in 2024, and that increases the number of bands to 25. That's going to be substantially bigger, but the problem is that data processing, each band that you collect, you have to process it, you have to maintain it, you have to store it. So yeah, it makes sense for them to try to keep the number of bands as low as possible.
I see. So it is sort of like a data processing and transfer limitation. Because I mean, you can buy cheap spectrometers that can collect like 50,000 bands.
Yeah.
You know.
I wish I knew. I'm one of those people where, yeah, I would need a lot of same thing. And the suspicion is that if we could get more samples from the spectral signature, we could have more successful predictions or model data integrations. But I have no, yeah, I wish there was more.
You might have to explain this, but maybe I missed it. It's complex and exciting words. I was wondering, are you constraining the error by forcing the model or reducing the uncertainty and forcing some constraint, or are you recalibrating the process-based model to predict the satellite data?
So the state data simulation, we don't change the parameters, so we don't need to restart the model from scratch from the planting day. But in the Bayesian framework, we take the model forecast as a prior, data becomes likelihood, we estimate the posterior distribution, and that posterior distribution represents that time step, and will be passed to the model to start from that time step to the next time step where we have that.
You have already simulated different scenarios or multi-models, and then you pick. So
We do it on the fly. So we're talking this morning about DSAT and AppSim and what's the difference. And this is exactly sort of what I had in mind, that AppSim allows us to do these kind of analysis on the fly without needing to
first start the simulation.
start the simulation or pause the simulation. So the system that we developed is over here. We built it on top of the regional modeling framework. So we would not be doing single site simulation. We would be able to run regional simulation like the cover crop showed you. But like the site studies that I showed you is just one single. We asked the regional system to be like, here is home. So all of this, I don't know if you're familiar, all of these are inside what's called a Docker container, which stores the requirement for model simulation itself. And then we allow for AppSim to talk to R code through C#, and that R code knows how to talk to Google Earth Engine to get soil moisture measurements or whatever measurements that we want. And it's sort of a streamline, moving the model forward in time and reading data from Google Earth Engine and incorporating. Sort of like a zip, two different sides, it just brings them all together.
All right, well, I think we're just about out of time now.